we have been discussing about the chapter solutions, keeping the fact in our mind that probably it is going to be the first chapter of the CBSE chemistry class 12 syllabus. But recently there has been changes from the CBSE itself. You should check the CBSE website for the latest chemistry syllabus, that the solid state which was earlier in our syllabus, which has been deleted, has been reintroduced from this academic session. So solid state will be there, which will be the first chapter. As usually solid state used to be the first chapter, but it was omitted, but it has been reintroduced. Anyway, solution we were carrying on, we have to carry on, then we will go back to solid state once again. So we were discussing the solubility of gases in liquids. We have discussed the Henry's law. Our next topic will be the vapor pressure of the liquid solutions. Now, whenever we talk about the liquid solutions, there are three options basically. Solubility of gases and liquids, which we have already discussed. Now, two things are left. One is the solid dissolved in liquid, where the liquid is the solvent and solute is the solid. Another is the liquid case, means liquid will be solute and the liquid will be solvent. So in this, we have to understand what is vapor pressure. Related to that, there is a law called Raoult's law. So all these things will be discussed today. So vapor pressure, liquid cases, solid liquid cases, and Raoult's law, that will be discussed today. In order to understand what is the vapor pressure of a liquid solution exactly, here we have chosen a closed container. This container over here is closed from everywhere. So here you can see the black portion is the liquid solution which we have taken, this one. And with time, this portion is vacant, means the liquid part is not there, the vacant space above the liquid within the container. So with time, the amount of liquid are going to evaporate and vapor is going to generate. And the vapor molecules will be here only in this region. So here I have kept that in red. So that will be in that region. It will put a pressure onto this liquid. With time, what will happen is that some number of liquid will keep on changing into vapor, and these vapor molecules, when they will come under the contact of the liquid, they will be condensed. So with time, what will happen is two simultaneous processes will go on gradually. One is the evaporation. So two processes will go on. One is the evaporation, and second is that the vapor pressure will come in contact with the liquid and they will be condensed. So that is condensation. Obviously, ultimately, a stage will be reached when the rate of the evaporation will become equal to the rate of the condensation. So here we can say the rate of evaporation will be equal to rate of condensation at some point of time. So when this rate will be same, then we can say the equilibrium is reached. So at that point, that means when the equilibrium will be reached, the pressure exerted by the vapors above the liquid surface at a given temperature is called the vapor pressure. So if we redefine the vapor pressure, it will be like the pressure exerted by the vapors above the liquid surface in equilibrium, that is very important, with the liquid at a given temperature is called vapor pressure. Now let us see the factors that governs the vapor pressure, or the amount of vapor pressure that will be generated. One is the nature of the solution. How, see, different liquids will have different intermolecular forces. So as you know, higher is the intermolecular forces, lesser will be the tendency to get vaporized. So it depends on their intermolecular forces, and different liquids will have different intermolecular forces. Second factor is the temperature. So in case of temperature, what happens? As we know, as the temperature increases, the larger will be the kinetic energy. So the tendency of the molecules to escape from the surface of the liquid will also be more. So these two factors, one is the nature of the liquid and the temperature, governs the vapor pressure, amount of vapor that will be generated. Now we are going to see the vapor pressure of liquid solutions. Now a liquid solution is formed, as we know, when the solvent should be liquid. That means here the condition is the solvent should be liquid, and of course the liquid solvent is usually volatile. So here the solute can be three types. It can be solid, it can be liquid also, and it can be gas also. So now from here on we will see these various cases. We have already seen gases and liquids. Now we are going to see what happens when solid or liquids will form will be used as a solute, and it will combine with the liquid. We are going to see the first case, which is the vapor pressure of the liquid solutions. About to see the vapor pressure of the liquid solutions in both the cases. In one case we will take liquid in liquid, in another case we are going to take solid in liquid. So as of now we are discussing vapor pressure of liquid solutions. Now as I have written this Raoult's law, actually this famous scientist, French scientist he was, at 1886 he has given a law which actually expresses the mathematical relationship of this particular case. So let us first understand what he has said. He has said that Raoult's law suggests that at a given temperature for a solution of volatile liquids, the partial vapor pressure of each component in solution is equal to the product of vapor pressure of the pure component and its mole fraction. So if we try to define the law in a much more simple way, let us see like this. We have to consider first of all a binary solution. Binary solution. So what is a binary solution? Here binary means of course we will take two liquids since it's a liquid case. So one is liquid A, another is liquid B. Now suppose for liquid A the mole fraction is XA, and for liquid B the mole fraction is XB. And similarly, if we consider the partial vapor pressure, that means for A the partial vapor pressure will be PA, and for B the partial vapor pressure will be PB. Now as per the Raoult's law, if here we can write PA0, that is vapor pressure of pure A, and similarly PB0 is vapor pressure of pure B, then we should be able to write as per the Raoult's law, because I would like to repeat this particular law once again. He has said that at a given temperature for a solution of volatile liquids, the partial vapor pressure of each component, that means he has said the partial vapor pressure of A will be equal to the product of the vapor pressure of the pure component and its mole fraction. So vapor pressure of the pure component is PA0 as we have written, into its mole fraction, that is XA. Similarly, we should be able to write that PB should be equal to PB0 as its vapor pressure of the pure B into XB. Along with that, we know that the sum of the partial pressure in the solution, that is PA plus PB, should be equal to P, means the total pressure, because Dalton's law of partial pressure suggests that the total pressure will be is equal to the sum of their individual partial pressures. So in this, if this is the equation number 1, we should be able to write that it should be PA means it is, here you can see PA0 into XA plus PB means PB0 into XP is equal to P. At the same point of time, we know that the mole fraction XA plus XP, because there are two components only, it should be 1. So XA should be 1 minus XB. So onto that equation, onto this equation, if we want to write, it should be like this: P is equal to PA0 into 1 minus XB plus PB0 into XP. So this is now 1 minus XB. It can also be written as, so PA0 we can write, and here we can see we can write P is equal to PA0 plus PB0 minus PA0 into XP. So here you can see this is the final equation from the Raoult's law, in which case again I would like to repeat that our cases was liquid-liquid case. We have chosen two liquids, its mole fraction, its partial pressure. Now we know the pure vapor pressure of A we have taken as PA0, then we have taken PB0. So we have written, as per the Raoult's law, we have written these two. Then as per the Dalton's law, this is Dalton's law, we can write the total pressure will be equal to the sum of the partial pressure. Then we have substituted the equations, then XA plus XB should be equal to 1. Then we are getting into this final equation, this one. So this is all about the mathematical expression of the Raoult's law for liquid-liquid cases. Now we are going to see its various aspects and its graphical representation. Let us see the graphical representation. I have drawn the graph already though. So I have written three important equations. One is this one for the case of liquid A only, this is for liquid B only, and this is the third one where the total pressure is represented as the addition of these two. Now see this graph carefully. Let us understand that in this, on this axis the vapor pressure is plotted. On this axis we have plotted the mole fraction. Now on this point, since it's a binary solution, so XA is 1, so of course XB has to be 0. Say this, if XA is 1 and XB is 0, so on this line, if you want to write that PA is equal to PA0 into XA, so here if XA is equal to 1, PA has to be PA0. Similarly, if PB is equal to PB0 into XB, if XB is equal to 1, PB will be equal to PB0. So here you see XA is equal to 1. That means PA, that is the vapor pressure, will be equal to PA0. So this point. And as slowly as you can see, at XA is equal to 0, for this XA is equal to 0, PA should also be 0. That is what we have got. So if XA is equal to 0, the vapor pressure will be 0. So see this line, the black one. This line actually represents the equation number 1. Similarly, this one actually represents the equation number 2. Let us see over here. This one suggests if XB is equal to 1, that means, sorry, this one should be XB is equal to 1. For XB is equal to 1, it is PB is equal to PB0. Here it is, if for XB is equal to 1, the vapor pressure is PB0. And on this point, if XB is equal to 0, so here also, if XB should be 0. So if here XB is 0, Pb should be also 0. So here we can see the vapor pressure slowly comes down to be 0. So this line represents equation number 2, that is this one, and this line represents equation number 1. The addition of these two, this is the red line which is 3, basically represents the addition of P, that is PA plus PB, which is nothing but XA PA0 plus XB PB0. So through this graph we have tried to explain that for these two separate cases, for liquid A and liquid B, how the graphs can be represented, and the summation of those two will be nothing but the equation number 3, which is the liquid-liquid solution for binary cases.